Hello students, today I will take the first chapter of the heat transfer, that is introduction and basic concept of the heat transfer. Then next we have to take objectives of that what are the heat transfer objectives are there, and those objectives we have to take. And objectives means here what we are going to study in this chapter, that is understand how thermodynamics and heat transfer are related to each other. Actually the thermodynamics is also a energy transfer, and that due to the temperature difference. But here the amount of heat transfer we are going to determine, but what time period that amount of heat transfer takes place, that is not possible to determine from that one. And also the direction of the heat transfer we are not going to get from that thermodynamics point of view. And that we are going to study here. Then distinguish the thermal energy from other forms of energy and heat transfer from the other forms of energy transfer. Actually here the heat and work are the main energy forms, and there are some other forms of the energy like that electrical energy, magnetic, gravitational, soft power, like that. There are many forms of energy are there, and those are related with the energy transfer as a heat transfer also. Then here we have to perform general energy balance equations. Whenever heat transfer takes place, energy balance equation we have to take, and from that we have to determine that how much energy transfer will take place and how that will be balanced. And after that understand basic mechanisms of heat transfer. The heat transfer takes place through the different mechanisms, and what are those different mechanisms we have to discuss. Those are the conduction, convection and radiation are the three mechanisms of heat transfer or modes of heat transfer. And from that, for the three modes of heat transfer, there are three laws concerned to these mechanisms of the heat transfer. Those are the first one is the Fourier Law of Conduction, and second one is Newton's Law of Cooling. Third one is Stefan Boltzmann law for radiation. Then identify the mechanism of heat transfer that occurs simultaneously in practice. In some of the cases, not only through the single mechanism the heat transfer takes place, the heat transfer will takes place by combination of the one or two or three mechanisms, and that combination also we have to identify, and from that whatever the rate of heat transfer is that also we can determine. Develop an awareness of the cost associated with heat losses. Okay, actually heat transfer equipments what we are going to take, actually the heat from the one fluid to the another fluid we want to transfer, there is some heat loss takes place. Due to that the additional cost whatever the occurs, that also we have to determine. In case of that will take place in boiling and condensation as well as in the heat exchangers. Solve the various heat transfer problems encountered in practice. Now we are going to determine the heat transfer problems. Then next one, thermodynamics and heat transfer. Okay, here the some definitions concerned to the thermodynamics and heat transfer will take. The heat is a form of energy that can be transferred from one region to the another as a result of temperature difference. Heat is a form of energy. Okay, then thermodynamics is concerned to the amount of heat transfer as it undergoes process from one equilibrium state to the another. Thermodynamics here amount of heat transfer we are going to energy transfer or heat transfer we are going to find out from that. Heat transfer is the transfer of heat from one region to the another region due to the temperature difference. There always requires a temperature difference, and from that temperature difference the heat transfer takes place. Okay, and due to that one whatever the heat is transferring, that we have to call as a heat transfer. Then here the heat is a form of energy, and due to the temperature difference heat will be transfer will take place. Then what is the temperature? The temperature will be a measure of hotness or a coldness. How much hot it is, how much cold it is the particular region or a particular system, that we are going to measure in terms of the temperature. Then the transfer of energy as a heat always from higher temperature medium to the lower temperature medium. The driving potential is the temperature difference here. Due to that higher temperature region to the lower temperature region, the heat transfer takes place. Then heat transfer stops when the two mediums reach the same temperature. That means the equilibrium temperature those will reach. Then the heat transfer will be takes, and the two systems will be in thermal equilibrium. That we can call from in the thermodynamics also we have discussed the same thing of the thermal equilibrium. heat can be transferred in three different modes. Already I told that what are the different mechanisms. Those are also called as the modes of heat transfer. Those are the conduction, convection and the radiation heat transfer. Then here the examples of this heat transfer, before going to take the different modes of the heat transfer, we are how the heat transfer is required. Okay, in the thermodynamics point of view, what we cannot determine and what is we can determine from the heat transfer point of view. Okay, here we can see that we are normally interested in how long it takes for the hot coffee in a thermos bottle to cool a certain temperature, which cannot be determined from the thermodynamic analysis alone. Okay, in the thermodynamics, what amount of heat will be transferred, that only we can determine. But for which period of time, for the what time that heat transfer, amount of heat transfer takes place, that we cannot determine. Okay, that for that point that heat transfer is required, which gives the time for the transfer of the particular amount of the heat transfer. And heat flows in the direction of decreasing temperature. Here we are telling that one, the heat transfer takes place in the direction of decreasing temperature, from the higher temperature region to from the lower temperature. That will be direction of the heat transfer. The direction of the heat transfer also we are going to get from this heat transfer point of view. These are some of the examples from the human body heat transfer takes place: air conditioning systems, heating systems and electronic equipment which are need to be cooled, and power plants, they are the heat cooling towers we are going to use to cool the whatever the this fluid is there. Then refrigeration system. Okay, these are the common examples we can say that where the heat transfer will takes place. Okay, and the whatever heat transfer is applied. Then now we'll go to what are the different mechanisms of the heat transfer. Heat transfer mechanism. In that first one is the conduction. Conduction is the mode of heat transfer in which heat transfer takes place from higher temperature region to the lower temperature region by kinematic motion or direct impact of molecules in case of solids, or by drift of free electrons in case of metals. Okay, here the heat transfer takes place direct impact of molecules. One molecule is attached with the other molecules. In case of solids, okay, there the heat is transferring from the one molecule to the another molecule. And in case of metals, there are number of free electrons are present in the case of metals, and these free electrons actually move to carry the heat. Actually the metals will remain solid only, the electrons only move. Atomic level the heat transfer takes place by the free electrons. In case of liquids, gases and liquids, conduction is due to the collisions and diffusion of the molecules during their random motion. In solids, it is due to the combination of vibrations of the molecules in lattice and energy transferred by the free electrons. That I told you that one, due to the direct impact of molecules, that is due to the vibration of molecules due to the higher temperature heat contained in that one. Then here the Fourier law of conduction, that is concerned to the conduction, that we can define here. The rate of heat conduction is directly proportional to the area normal to the heat transfer and temperature gradient in that direction. That is the Fourier law of conduction, the law concerned to the conduction mechanism of the heat transfer. Here we can say that when this is the conduction, this is the conduction. Here the heat is transferring from higher temperature to the lower temperature. The higher temperature T1 is there, lower temperature T2. From this one heat is transferring and area normal to this one, and this is the this whatever is the distance, that is the dx, the x is increasing in this direction. Okay, then here we can write the q is directly proportional to the area normal to the heat transfer and temperature gradient. Okay, the area normal to the heat transfer, the normal, okay, the right angles to that heat transfer, whatever the area is there, okay, to that it is proportional, and temperature gradient, change in temperature with respect to particular distance, that is temperature gradient. Okay, that is dt by dx is the temperature gradient. Then we can say that one q is equal to k dt by dx. Then here q conduction, that if you simplify this equation, we are going to get that is k dt is a t1 minus t2 and dx is a delta x, that is a change in distance. That we can write minus k delta t by dx. Here the negative sign we are going to take because of that one. In the direction of heat transfer, the temperature decreases. And where the k is the thermal conductivity. It is a constant of proportionality, that is the thermal conductivity. That can also be defined. Okay, that q conduction we can write minus k dt by dx. This is a Fourier law of conduction. Then here the K whatever is there, that K we can define a measure of the ability of the material to conduct heat. It is the ability of the material to conduct heat. Then the temperature gradient. The temperature gradient whatever is the dt by dx, that is the slope of the temperature curve on a Tx diagram. It is the slope. Okay, whatever the slope is there, that is the dt by dx is the slope of the temperature curve on a Tx curve. Heat is conducted in the direction of decreasing temperature, and the temperature gradient becomes negative when temperature decreases. Okay, here conducting in the decreasing temperature, therefore the temperature gradient becomes negative if the temperature is decreasing. The negative sign in the equation ensures that heat transfer is in the positive x direction and is positive quantity, and the heat transfer will not be negative, but the heat transfer is a positive quantity, and due to that decreasing temperature we are going to take the negative sign. A heat conduction analysis represents area normal to the heat direction. Okay, here the area normal to the heat transfer, the what area we are going to take. Okay, the normal area, this is area is equal to width into height. This is the area normal to the heat transfer, and the temperature gradient here we can write 1 meter length. That 1 meter length will be the dx. We are going to get, that is dx as a change in distance or a distance in which the heat is transferring. Then thermal conductivity, already we know that the rate of that also defined as the rate of heat transfer through unit thickness of the material per unit area per unit temperature difference. Already we know that the thermal conductivity of a material is the ability of the material to conduct heat. Okay, that also we can determine, and its value indicates that one higher value of the if it is thermal conductivity is that material is a good heat conductor. If it is a lower value of the thermal conductivity, if it is there, then that will be the material is a poor conductor of a heat. And here the one of the experimental setup is given, the simple experimental setup to determine the thermal conductivity of the material. And here the experimental this experiment we are going to conduct in our laboratory also to find the rate of heat transfer. By using the Fourier Law of Conduction, we are going to determine the thermal conductivity and what amount of heat is transferring to this one to conduct the heat. That we know as we are going to supply the electricity, so that from that we can find out the whatever the thermal conductivity is there. Okay, here the thermal conductivity of the sum of the material are given. The highest thermal conductivity is there for the diamond 23,000, silver it is 429, copper 401, and this 401, copper 401, gold it is 317, aluminum 237, like that it will be decreasing for the different materials. Okay, and that in which range the thermal conductivity the different materials are present, that is gases here comes, and later fibers, wood, like that, mercury, water, liquids will come. Okay, then whatever the oxides and rocks, some other materials, then comes metals, aluminum, bronze, then silver, iron and manganese, diamond, graphite, silicon, beryllium oxide and quartz. These are the highest thermal conductivity, and this is the variation of this thermal conductivity with at room temperature, what is its thermal conductivity is there for the different materials. Then thermal conductivity of the gases such as air varies factor of 10⁴ from those pure metals such as copper. Okay, its variation is very higher for this thermal conductivity of the gases compared to the copper metals. Okay, like that the pure alloy metal, that's for this thermal conductivity what is there, that will be at 300 Kelvin, those are given. Okay, for different also these are given, and here how the conduction will take place in terms of the gases, okay, in terms of liquids, and in case of the solids, how the heat transfer by the conduction will take place in the gas and in liquid and solids. Okay, that is explained here. Then the whatever the variation of the thermal conductivity also given here for the different materials with the temperature. Here the variation of the thermal conductivity will take place with the temperature. The thermal conductivity of the solids will increase with the increase in the temperature, but it will decrease for the gases. Thermal diffusivity, another terms comes here for the thermal conduction, that is the thermal diffusivity. The thermal diffusivity is given as the ratio of the heat conduction to the heat storage. How much conduction of the heat takes place to the how much it will stores, that we can defined from this thermal diffusivity, that is the diffusion of the heat. The K by rho Cp we can take from that one. Then K by rho Cp, here the Cp is the specific heat, then rho Cp is the heat capacity, alpha is thermal diffusivity, K is the thermal conductivity. The material that has a higher thermal conductivity or low heat capacity will obviously large thermal diffusivity. High thermal conductivity if it is there, and low whatever the heat capacity or heat storage if it is there, then the higher thermal diffusivity it will have. The larger thermal diffusivity, faster will be the propagation of the heat into the medium. The diffusion will be takes place more faster. The smaller value of the thermal diffusivity means that heat is mostly absorbed by the material and small amount of heat is conducted further. Okay, here the absorption of the heat takes place if it is a lower diffusivity present. Then next mechanism of the heat transfer is the convection. The convection is the mode of heat transfer from high temperature region to the low temperature region by kinetic motion or molecular motion. Okay, here actually the molecular move to the transfer the heat. In this case of the liquids and the gases, the actual molecules will move to carry the heat. Whatever in case of solids, the molecules will not move, but in the liquids and gases, the molecules will move to the transfer the heat. That is the convection mode of the heat transfer. And here from solid surface to the fluid and vice versa, or within the fluid, whatever the heat is transferring, that will call as a convection mode of the heat transfer. The higher the fluid motion, the greater convection heat transfer takes place. That is depending upon the fluid motion also, and if it is a higher the fluid motion if it is there, then the higher will be the heat transfer takes place by the convection. In the absence of the bulk fluid motion, the heat transfer between the solid and adjacent fluid will be by pure conduction. Here the fluid is stationary. If there is no movement of the fluid, then the heat transfer takes place by the conduction instead of the convection. Here we can see that one, the air velocity at the surface, it is 0, and that will go on increasing, and there the heat transfer takes place from the hot surface to the surrounding air, and the temperature at the surface is higher and go on in decreasing. This one, this is the velocity and this is the temperature for the heat transfer from the surface to the surrounding fluid. Then here this convection heat transfer are of the two types. One is the forced convection. If the fluid movement is there, the fluid movement is required to transfer the heat. If the fluid movement is by the external means or external sources such as fan, pump or a blower, then that is known as a forced convection. If the fluid motion is caused by the buoyancy effect forces that are induced by the density difference due to variation of temperature in the fluid, okay, that is by naturally the movement of the fluid takes place or free of the external forces. If the fluid movement takes place, then that is the natural convection. We can take here that one, okay, it is the forced convection. Here by the fan, air is blowing over this object, and here the naturally the air is moving over that one, so that from this hot object to the surrounding air, the heat transfer takes place. Heat transfer process that involves change of phase. The change of phase, whatever is there, that is the boiling and the condensation. There also heat transfer takes place by the whatever this convection mode of heat transfer. And concerned to this convection, the law concerned whatever is there, that is the Newton's law of cooling. As the rate of heat transfer by convection is directly proportional to the surface area and temperature difference. Okay, here the rate of heat transfer by the convection is directly proportional to the surface area from which heat is transferring or to which heat is transferring. Okay, and the temperature difference, that we can write as a Q convection is equal to HAS Ts minus T infinity. Then H is a convective heat transfer coefficient, AS is a surface area through which it is transferring, and Ts is a surface temperature, T infinity is a surrounding fluid temperature or a ambient temperature. Then convective heat transfer coefficient H, whatever is there, the convective heat transfer coefficient H is not property of a fluid. It is not a property of a fluid. It depends upon the different parameters. Okay, and that is, it is experimentally determined for the some of the simple surfaces, and it will be determined that is by using the mathematical formulation for the complex systems, and that is depending upon the geometry of the surface, the nature of the fluid motion, the properties of the fluid, bulk, fluid velocity. For on all these, the whatever the heat transfer coefficient is there, that is defined. And this heat transfer coefficient, what are there for the different fluids? Okay, it is given. Free convection of the gases 2 to 25, free convection of the liquid 10 to 1000, force of convection is 25 to 50 for the gases, force convection for liquids 50 to 20,000, and boiling and condensation it is a 22,500 to 1 lakh watt per meter square degree Celsius. Then radiation. The radiation is a mode of heat transfer in which heat transfer takes place by the electromagnetic wave phenomenon or by the electromagnetic waves. We can call as photons also. As a result, whatever the change in the electronic configuration of the atoms or molecules takes place, due to that the heat transfer takes place. And here the radiation, that is not required any intervening medium. Okay, for the conduction, the solid medium is required. For the convection, fluid medium is required, either liquid or gases. But here there is no medium is required, even though through the vacuum also the radiation heat transfer takes place. In fact, the heat transfer by radiation is fastest, and it suffers no attenuation in vacuum. In vacuum also it will transfer. This is how the energy from the sun reaches the earth. From the sun, earth, whatever the heat transfer is there, it is one of the best example for the radiation heat transfer. Because of up to the certain distance, there is a earth atmosphere is there. Behind that there is no medium. Through that also the heat transfer takes place from the sun to earth, that is by the radiation. In the heat transfer studies, we are interested in thermal radiation, which is from the radiation emitted by the bodies of their temperature. Okay, here the emitting the heat by the radiation from the certain bodies due to their temperature, that we are going to find out. And all the bodies temperature above the absolute zero emit thermal radiation. Absolute zero temperature, whatever the bodies if it is present, then those will emit the radiation. Radiation is the volumetric phenomenon, and all solids, liquids and gases emit, absorb and transmit the radiation varying degrees. However, the radiation is usually considered to be surface phenomenon for solids. From the surface only the radiation heat transfer takes place, and within that body there is no radiation heat transfer. Then concerned to the radiation heat transfer, the law is the Stefan-Boltzmann law. Okay, the Stefan-Boltzmann law states that the energy emitted by a black body is directly proportional to the fourth power of its absolute temperature. The energy emitted by a black body is directly proportional to fourth power of its absolute temperature. That is, the Q is directly proportional to Ts raised to 4, and sigma and As we are included. The sigma is a Stefan-Boltzmann constant, As is a surface area. And this equation holds good for the idealized black body. That means the black body which will emit 100%, which will absorb if the radiation is falling on it, the 100% emitter and the 100% receiver black body. If the surface is not a black, okay, it is not 100% emitting its radiation, it is having the particular emissivity. Q emit is equal to emissivity epsilon sigma A Ts, radiation emitted by the real surfaces, where the emissivity is included. That emissivity is a measure of how closely a surface approximately black body, for which epsilon is equal to 1 for the surface, and of the surface here the epsilon varies from the 0 to 1, and here the epsilon whatever is there, and that is 1 for the black surface, and it is varies 0 to 1 for the other surfaces. It is whatever the emissive power of a surface to the emissive power of a black body. Okay, it is the ratio of the emissive power of a surface to the emissive power of the black body. And here we can say that the black body radiation represents the maximum amount of radiation that can be emitted from a surface at a specified temperature. Okay, then black body emissivity is this one. It's surrounding Q emit max, we can sigma Ts square, and the temperature is given, its surface is 400, and if you calculate from that one by using this Stefan-Boltzmann constant, the 52 watt per meter square as per meter square area we are going to determine. Then absorptivity, and we have to take from that only. The absorptivity, this is later comes in the radiation chapter, but we'll take the little about that one. The how much amount of the radiation absorbed by the body is called as the absorptivity, and black body absorbs the entire radiation when incident on it. If it will incident radiation energy on it, it will be absorbed all the radiation. The Kirchhoff's law, the emissivity and absorptivity of the surface at a given temperature and equal. Temperature and wavelength are equal. Okay, here the emissivity and absorptivity for the given temperature and the wavelength are equal. Okay, here just we can say that one, absorptivity and emissivity both are equal for the surfaces. Okay, for the particular wavelength if it is present, and here the emissivity of the different materials are given. Okay, here net radiation exchange. Here till now we have taken from the radiation emitting from the black body or actual surface, but here the exchange between the two bodies if it takes place, then what will be the radiation heat exchange here we have to take. And this equation whatever is there, here is the one solid body that is exchanging with the surrounding area, surrounding environment. Okay, then surrounding the another surface we will take there. The exchange of the heat between these two takes place by the radiation, and Q radiation can be written as the emissivity epsilon sigma as Ts raised to 4 minus of T surrounding raised to 4. The surrounding temperature also we are going to consider instead of its surface temperature only. Okay, by that one, whatever the amount of heat exchange takes place between the surrounding and the particular body by the radiation, that also we can determine. Net radiation heat transfer we will call, that is the difference between the rates of heat radiation emitted by the surface and the radiation of top. And the determination of net rate of heat radiation by between two surfaces, complicated matter since it depends upon so many parameters, that properties of the surfaces, the orientation and relative to each other, interaction of the medium between the two surfaces with radiation. Radiation is usually significant relative to the conduction and convection, natural convection, but negligible relative to force of convection. And surface is completely enclosed by a much large black surface at a temperature T surrounding, then separated by gas that does not interact with the radiation. The net rate radiation heat transfer between these two surfaces given by this equation we can write for that one. Okay, actually later we will take that is the orientation and the properties of the surfaces all while taking the radiation. Then when radiation occurs simultaneously with the combined whatever the convection mode of heat transfer, here the combined convection heat transfer coefficient we are going to take. The combined heat transfer coefficient will be H convection, H radiation, H convection can be written as H convection only, and H radiation will be, that can be epsilon sigma Ts plus of T surrounding, Ts square plus of the T surrounding square. By using this one H combined we can determine, and combined heat transfer we can, the combined convection and radiation heat transfer we can find out from this. And here we studied in this part the heat transfer mechanisms, the conduction, convection and radiation. In the conduction we have determined Fourier law of heat conduction and thermal conductivity, thermal diffusivity, and convection Newton law of cooling we find out, and heat transfer coefficient, convective heat transfer coefficient, and radiation in that Stefan-Boltzmann law we have taken. And from that the simultaneous heat transfer mechanisms also we have taken, and the problem solving technique. Here some techniques or packages are used to solve the heat transfer problems. That's not concerned to us, that is a heat transfer mechanism we are going to use. Okay, thank you all. We will continue in the next part. Thank you.